Hi friends, we have discussed combinational logic circuits at length in previous lectures, and the focus in the present and some of the next lectures will be on sequential logic circuits. While a logic gate is the most basic building block of combinational logic, its counterpart in sequential logic is the flip-flop. We will begin with brief introduction to different types of multivibrators, including the bistable multivibrator, which is the complete technical name for a flip-flop, the monostable multivibrator and the astable multivibrator. The flip-flop is not only used individually for a variety of applications, but it also forms the basis of many more complex logic functions. Two categories of bistable devices are the latch and the flip-flop. Bistable devices have two stable states called set and reset. They can retain either of these states indefinitely, making them useful as storage devices. The basic difference between latches and flip-flops is the way in which they are changed from one state to the other. The flip-flop is a basic building block for counters, registers and other sequential logic, and it's used in certain types of memories. The monostable multivibrator, commonly known as the one-shot, has only one stable state. A one-shot produces a single controlled width pulses when activated or triggered. A astable multivibrator has no stable state and is used primarily as an oscillator, which is a self-sustained waveform generator. Latches. The latch is a type of temporary storage device that has two stable states and is normally placed in a category separate from that of a flip-flop. Latches are similar to flip-flops because they are bistable devices that can reside in either of two states using a feedback arrangement in which the outputs are connected back to the opposite inputs. The main difference between latches and flip-flops is the method used for changing their state. A latch is a type of bistable logic device or multivibrator. An active high input SR or the set reset latch is formed with two cross coupled NOR gates as shown in figure A, and an active low input SR latch is formed with two cross coupled NAND gates as shown in figure B. Notice that the output of each gate is connected to an input of the opposite gate. This produces the regenerative feedback that is characteristic of all latches and flip-flops. To explain the operation of the latch, we will use the NAND gate SR latch in figure B, and this latch is redrawn with a negative or equivalent symbol used for the NAND gates. This is done because lows on the S and R lines are the activating inputs. This latch has two inputs S bar and R bar and two outputs Q and Q bar. Let's start by assuming that both inputs and the Q output are high. Since the Q output is connected back to an input of gate G2 and the R bar input is high, the output of G2 must be low. The low output is coupled back to an input of gate 1, ensuring that its output is high. When the Q output is high, the latch is in the set state. It will remain in this state indefinitely until a low is temporarily applied to the R bar input. With the low on the R bar input and a high on S bar, the output of gate G2 is forced high. The high on the Q bar output is coupled back to an input of G1, and since the S bar input is high, the the output of G1 goes low. This low on the Q output is then coupled back to an input of G2, ensuring that the Q bar output remains high even when the low on the R bar input is removed. When the Q output is low, the latch is in the reset state. Now the latch remains indefinitely in the reset state until a low is applied to the S input. In normal operation, the outputs of latch are always complement of each other. That is, when Q is high, Q bar is low, and when Q is low, Q bar is high. An invalid condition in the operation of an active low input SR latch occurs when lows are applied to both S bar and R bar at same time. As long as the low levels are simultaneously held on the inputs, both the Q and the Q bar outputs are forced high, thus violating the basic complementary operation of the inputs. Also, if the lows are released simultaneously, both outputs will attempt to go low. Since there is always some small difference in the propagation delay time of the gates, one of the gates will dominate in its transition to the low output state. This in turn forces the output of the slower gate to remain high. In this situation, you can reliably predict the next state of the latch. Table here summarizes the logic operation in truth table form. Logic symbols for both the active high input and the active low input latches are shown in figure. An application. A good example of an application of an SR latch is in the elimination of mechanical switch contact bounce. When the pole of a switch strikes the contact upon switch closure, it physically vibrates or bounces several times before finally making a solid contact. Although these bounces are very short in duration, they produce voltage spikes that are often not acceptable in digital systems. This situation is illustrated in figure A. The S bar R bar latch can be used to eliminate the effects of switch bounce as shown in part B of figure. The switch is normally in position 1, keeping the R bar input low and the latch reset. When the switch is thrown to position 2, R bar goes high because of a pull up resistor to VCC, and S bar goes low on the first contact. Although S bar remains low for only a very short time before the switch bounces, this is sufficient to set the latch. Any further voltage spikes on the S bar input due to switch bounce do not affect the latch and remains set. Notice that the Q output of the latch provides a clean transmission from low to high, thus eliminating the voltage spikes caused by contact bounce. Similarly, a clean transition from high to low is made when the switch is thrown back to position 1. The gated SR latch. The figure shows the logic diagram and logic symbol for a gated SR latch. A gated latch requires an enable input En. The S and R inputs control the state to which the latch will go when a high level is applied to the enable input. The latch will not change until enable is high, but As long as it remains high, the output is controlled by the state of the S and R inputs. In this circuit, the invalid state occurs when both S and R are simultaneously high. The gated D latch. Another type of gated latch is called the D latch. It differs from the SR latch because it has only one input in addition to enable. This input is called the D or the data input. When the D input is high and the enable input is high, the latch will set. When the D input is low and enable is high, the latch will reset. Stated another way, the output Q follows the input D when enable is high. Edge triggered flip flops. Flip flops are synchronous bistable devices, also known as bistable multivibrators. In this case, the term synchronous means that the output changes states only at a specified point on the triggering input called the clock, which is designated as a control input C. That is, changes in the output occur in synchronization with the clock. An edge triggered flip flop changes state either at the positive edge, that is rising edge, or at the negative edge, that is falling edge of the clock pulse, and is sensitive to its inputs only at the transition of the clock. Three types of edge triggered flip flops are covered in this section: SR, D, and JK. Although the SR flip flop is not available in IC form, it is the basis for the D and JK flip flops. Notice that each type can be either positive edge triggered or negative edge triggered. The key to identify an edge triggered flip flop by its logic symbol is the small triangle inside the block at the clock input. This triangle is called the dynamic input indicator. The edge triggered SR flip flop. The S and R inputs of the SR flip flop are called synchronous inputs because data on these inputs are transferred to the flip flop's output only on the triggering edge of the clock pulse. When S is high and R is low, the Q output goes high on the triggering edge of the clock pulse and the flip flop is set. When S is low and R is high, the Q output goes low on the triggering edge of the clock pulse and the flip flop is reset. When both S and R are low, the output does not change from its prior state. An invalid condition exists when both S and R are high. Remember, the flip flop cannot change state except on the triggering edge of a clock pulse. The S and R inputs can be changed at any time when the clock input is low or high, except for a very short interval around the triggering transition of the clock without affecting the output. The edge triggered D flip flop. The D flip flop is useful when a single data bit 1 or 0 is to be stored. The addition of an inverter to an SR flip flop creates a basic D flip flop as shown here. Notice that the flip flop in figure has only one input, the D input in addition to the clock. If there is a high on the D input when a clock pulse is applied, the flip flop will set and the high on D input is stored by the flip flop on the positive going edge of the clock pulse. If there is a low on the D input when the clock pulse is applied, the flip flop will reset and the low on the D input is stored by the flip flop on the leading edge of the clock pulse. In the set state, the flip flop is storing a 1, and in the reset state it is storing a 0. The logical operation of the positive edge triggered D flip flop is summarized in this table. The operation of a negative edge triggered device is of course the same, except that triggering occurs on the falling edge of the pulse. Remember, Q follows D at the active or triggering clock edge. The edge triggered JK flip flop. The JK flip flop is versatile and is widely used type of flip flop. The functioning of the JK flip flop is identical to that of the SR flip flop in the set and reset and no change conditions of operation. The difference is that the JK flip flop has no invalid state, as does the SR flip flop. Figure here shows the basic internal logic for a positive edge triggered JK flip flop. It differs from the SR edge triggered flip flop in that the Q output is connected back to the input of gate G2 and the Q bar output is connected back to the input of G1. The two control inputs are labeled J and K in honor of Jack Kilby, who invented the integrated circuit. A JK flip flop can also be of the negative edge triggered type, in which case the clock input is inverted. Let's assume that the flip flop shown in figure is reset and the J input is high and the K input is low rather than as shown. When a clock pulse occurs, a leading edge spike indicated by 1 is passed through gate G1 because Q bar is high and J is high. This will cause the latch portion of the flip flop to change to set state. The flip flop is now set. If you make J low and K high, the next clock spike indicated by 2 will pass through the gate G2 because Q is high and K is high as well. This will cause the latch portion of the flip flop to change to reset state. If you apply a low to both the J and K inputs, the flip flop will stay in its present state when a clock pulse occurs. A low on both J and K results in a no change condition. So far, the logical operation of the JK flip flop is the same as that of the SR type in the set, reset and no change modes. The difference in operation occurs when both the J and K inputs are high. To see this, assume that the flip flop is reset. The high on Q bar enables gate G1. So the clock spike indicated by 3 passes through to set the flip flop. Now there is a high on Q which allows the next clock spike to pass through G2 and reset the flip flop. This table here summarizes the logic operation of the edge triggered JK flip flop in truth table form. Notice that there is no invalid state as there is with the SR flip flop. The truth table for a negative edge triggered device is identical except that it is triggered on the falling edge of the clock pulse. So friends, that brings us to the end of our discussion in this lecture, and therefore we sum up. In this lecture, we learned that two categories of bistable devices are the latch and the flip flop. Bistable devices have two stable states called set and reset. They can retain either of these states indefinitely, making them useful as storage devices. The basic difference between latches and flip flops is the way in which they are changed from one state to the other. The flip flop is a basic building block for counters, registers, and other sequential control logic, and is used in certain types of memories. So, that is it for today. See you in the next lecture with more on logic circuits. Thank you very much.